Thank you. Greeting everyone, I'm Mnijli, and I'm here to present my paper, which was conducted within Mira institution in collaboration with ESTIA and Tunis. So basically, in today, e-health system solutions are evolving and increasingly relying on using IoT devices and TMIS application, which transforming the patient-doctor relationship. And they're improving the healthcare management. And with this technology, we can use and of course follow up the patient real time. And of course, we can get more personalized, suitable treatment. And in this context, we have wireless body area network, which plays a crucial role, which is basically body-worn sensors wirelessly connected between sensors to exchange data. And they're actually transferring sensitive data such as healthcare, biometric information, and more. And now, why is it important to secure data exchange? We can take here an example where we have sensor nodes exchanging data and everything works fine with personalized care. However, if an attacker can get access to one of these nodes, he can inject false data, which can cause inappropriate care or risk for the patient. Now, that's because the limitation resources in this network, because it's limited to energy, consumption, and memory and computation. And here the challenge is to find balance between robust security and low resource consumption. Now the solution is to use biometric. And biometric, we mean heart rate. With the use of physiological signals, we can capture the heart rate and use it to generate a cryptographic key to which is unique to secure medical system. These keys are main advantages are unique for each individual with a specific fingerprint, always available to collect, and of course, lightweight. Now, other solutions have already explored the use of the biometric solutions, and mainly the ECG. However, most of these studies have remained theoretical, with only the use of simulated dataset. Of course, at first, we studied the use of the ECG, electrocardiogram, which is a reliable solution. However, it requires a specific placement for electrode. That will cause problems if we want to integrate it into a lightweight embedded system. And to make our solution even more reliable, we choose to use PPG sensors, which is another way to another biometric measurement where we can detect the blood movement with light. Now the solution is to capture heartbeat signals with PPG sensors, and each node will generate a unique biometric key in order to enable secure communication between each node. Now, to arrive at our final destination, to find a full wireless body area network integration with secure communication, we started with this paper as a proof of concept to validate that real-time PPG-based biometric approach to key generation is feasible and is an establishment as a foundation for full integration into other systems. Now, how this works? We have a PPG sensor that's going to collect a place on a finger, for example, that's going to collect heart rate signals. After that, the peaks are being detected and the IPI is calculated. It means intervals interval, and it means that we can detect the difference measurement of time between two peaks, consecutive two peaks. After that, these values of IPI gonna be converted into binary with specific lightweight algorithm. Now, this is a basic test where we implemented two sensors each connected to a microcontroller. Everyone's gonna collect heartbeat signals, generate a binary sequence, and we established a similarity test for two sensors across the same body, and a uniqueness test between two sensors on two different people to confirm the feasibility of this. For this experimental setup, we use a USB microcontroller with 4 PPG signals, sensors. Now, for our results, with starting for the first test, with 4 sensors placed on the same person, we can see that these signals are somehow aligned and similar. And of course, for the IPI values, it's still remains with a narrow range. Like it's a bit similar between each difference between each 2 peaks. However, for 2 sensors collected on 2 different people, we can see that these signals are completely different. And there's a large variation between the IPI values, which confirm the dissimilarity of the collected keys and generated keys. Now, for our results, we calculated the KDR, which is the key disagreement rate, which is mainly the number of difference of bits between 2 different keys. The blocks in red represent 2 keys, the comparison between 2 keys on 2 different people, which shows a high dissimilarity. However, the blue ones represent 2 keys on the same person, which is less probably than 10%. And where we come to an average KDR for 344 for the same person, and 4106% for 2 different persons. Now, what makes our solution even more better is, compared to other solutions, we do not use heavy signal processing, like wavelet denoising or clustering or error correction code. However, we use a lightweight method with Butterworth filter only, which allow it to be implemented in a hardware embedded system for IoT devices. Of course, we found a better result with 3.44 for same user compared to 5.9, and we tried to test it on multi-user, not just on 2 persons. We tried to test it on several people. Now, in conclusion, we confirmed that we can make real-time PPG-based biometric token lightweight generation and reliable for WBAN. And of course, same user means similar keys, different user, it means distinct keys with ensuring the robustness of these key generation. And of course, for perspective, we're willing to fully integrate this into hardwares, and we've integrated to other security systems like IoT devices or wearable devices. And of course, install it with testing, with performance under motion, and process variation, with resistant to noise and temperature, lighting, and multi-sensor interface. Thank you for your attention.